Welcome to The Explainer. Today, we are cracking open a really powerful idea from Saunders Maclean's legendary book, Categories for the Working Mathematician. Our mission? To uncover a universal pattern, a hidden blueprint that connects some of the most fundamental structures in all of mathematics. So our guide for this journey is an absolute classic, a real cornerstone of modern math. We're going to be focusing on a key concept from Chapter 7, the monoid. Now, on the surface, it seems pretty simple, but as you're about to see, this one little idea is like a secret key that unlocks a hidden unity across huge areas of mathematics. All right, so let's start with the basics. What is a monoid? I guarantee you've used them probably thousands of times without even knowing what they were called. They're one of the most basic, most common structures you can find. Okay, so what do you need to build one? It's actually a pretty simple recipe. You just need three things. First, you need a collection of stuff, a set. Second, you need a way to combine any two things from that set. And finally, you need two simple rules to hold true, something called associativity, and you need a special identity element that basically does nothing. Think about this. It's something we all know. The integers in addition, right? You can add any two integers together. It doesn't matter how you group them. 2 plus 3 plus 4 is the exact same as 2 plus 3 plus 4. And of course, there's 0. Adding 0 to any number doesn't change it. That makes it the identity. And there you have it. That's a perfect classic monoid. Okay, so that's the standard textbook definition. But now we're going to flip the script and look at this from a totally different and way more powerful angle. This is the category theory way of thinking. And the big idea here is to just stop caring about the individual elements. Instead, we're going to focus only on the operations and how they relate to each other. It's a shift from what things are to what things do. So this brings up a huge question. Is it even possible to describe the entire structure of a monoid, all of its rules, without ever talking about a specific element like 2 or -5? And the answer, amazingly, is yes. We can do it by turning these algebraic rules into simple diagrams of arrows. So let's take that associativity rule. We all know x times y times z is the same as x times y times z. In this new language, we can draw this rule. Imagine you have two different paths to get from point A to point B. One path is doing x times y first. The other path is doing y times z first. The rule of associativity just says, hey, both of these paths have to lead to the exact same destination. And it's the exact same story for the identity rule. Combining something with the identity element is just like not doing anything at all. In our diagram, this just means that the path for combining with the identity is the same as the path for doing nothing. So see, we've now described all the rules of a monoid using just these diagrams of arrows, no elements needed. Okay, this is really the key. We just managed to define what a monoid is, using only diagrams of arrows. We completely threw out the elements. And getting abstract like this is what lets us make a really powerful conceptual leap. This immediately begs the question, what if we're not in the familiar world of sets anymore? Our diagrams worked great there, but what if we're in a completely different mathematical universe? One with a totally different way of combining things. And that brings us to this big idea, a monoidal category. Now, don't worry about the jargon. All this means is any system, any category, that has some kind of product-like operation and some kind of unit object. The only rule is that those diagrams we just drew, the ones for associativity and identity, still have to work. The system itself can be made of anything, not just sets. Okay, so we have all the pieces on the board now. We've got a definition of a monoid that only uses diagrams, and we have this idea of a monoidal category, which is basically any world where those diagrams are allowed to live. This is where it all comes together. You don't have to take my word for it. Maclean himself points us right to the punchline. He says that a monad, which is this super important concept in things like functional programming, is, quote, just a monoid that happens to live in a different kind of category. The pattern is exactly the same. And boom, here it is. This is the big aha moment. Do you recognize this diagram? It's the exact same associativity diagram we saw before. The structure of the rule is identical. All we've done is swap out our specific set for a generic object C and our normal product for a generic product cross. The blueprint is the same. So this is the big payoff. A monoid isn't just one type of thing. It's a structural pattern. It's any object in any monoidal category that has these multiplication and unit arrows that follow the rules of our universal diagrams. Okay, so that's pretty abstract. What does this actually get us? Well, it reveals this incredible hidden unity across what seem like totally different parts of math. Let's just look at this table to see it in action. If our world is the category of sets, and our product is the regular old Cartesian product, then our universal pattern gives us a plain old monoid, right where we started. But what if we change the category? What if we're in the world of a billion groups, and we use a different kind of product called the tensor product? Suddenly, that exact same pattern defines a ring. Or what if we're in a world of functions, where the product is just composition? The pattern gives us a monad. Just let that sink in for a second. A monoid, a ring, and a monad. These three things that we learn about in totally separate classes that seem to have nothing to do with each other are actually just different costumes for the exact same underlying structure. And this isn't just some clever little observation. MacLean says it himself, right in the preface of the book. He says the idea of a monoid is absolutely fundamental to the entire subject. It's that important. So why does all this matter? It matters because this high-level abstract viewpoint gives us this incredibly powerful lens. It's like a universal language that lets us spot these deep connections that we'd completely miss otherwise. It's all about finding the one blueprint behind many different buildings. And that leaves us with one final, kind of mind-bending question. We just saw that a monoid or ring and a monad are, in a very deep sense, the same thing. It just makes you wonder, if we look at the world through this lens, what other things in math, or even outside of math, are secretly just different versions of the same deep universal pattern? What else is secretly the same?